Thank you very much for joining us this afternoon for the last of the workshop sessions. I'm Suha Casey. I'm Handium Application Specialist for North America, actually. And joining me here is Dr. Kristina de Paris. She has a very exciting subject that she will tell us all about, her work in Africa. I'm going to talk a little bit about what Handium is, a very, very brief introduction. So we were founded in 2011. We are in Quebec City, Canada. We are the life science industry, and we do actually cytometers, and we are specialized in microfluidics. We do have two offerings. We have the HPC 100, which is the one that is in Africa and which Dr. Paris will talk about. It is a sheathless instrument. It does not use sheath. We have, however, our new instrument. It is the 150 microsheath, and it uses 125 mil of sheath and therefore generates a very little waste also. The differences between them is very minute. The sheathless instrument, the flow cell, is a 50 by 50 by 100. We increased that size to a 75 by 75 by 100 in order to accommodate the sheath. The other difference is, while in the sheath we have to be very, very cautious about the cell concentration, and we could only run about 500,000 per mil, we have increased that concentration up to 10 million per mil at this time. At 1,000 events per second and 2,000 events per second, which is increasing up to 10,000 events per second at this time. The sheath instrument, sheathless, of course, does not use sheath. The microsheath, we use only a 10-to-1 ratio versus the 100-to-1 for the bigger instruments. And hence, a much less volume is used and a lot less waste is generated. We do have an option in the sheathless instrument that we actually recover our sample. This option goes away with the sheath instrument right now because now it's a diluted sample. Laser alignment, never in either of these, and I'll talk about that in the next slide. They are both portable. They are still very robust and goes everywhere. The fluid bottles, we have 3 in the sheathless instrument at 60 mil per bottle, and we have 2. One is the sheath bottle, and the other one is the rinse in the sheath instrument. So the heart of our instruments basically is the flow cell. And the flow cell is a fiber optic base that is laid down in a chip, and you have one that going across, which is basically the sample fiber optic, where we have a very precise drilled flow cell right in the middle. And the 2 blue fibers that you see here is actually the excitation fibers and the collection fiber. This fiber butts up against the flow cell itself, and that way there is no alignment required because the laser is directed directly to that interrogation point without having to do any kind of alignment. So we do not have free space optics and lasers. It is all directed via fiber optics. So what that allows us to do is have now uniform illumination of the flow cell. We actually have laser signal-to-noise conditioning is possible because of that. And the cells really do not have to be perfectly centered because we have a little bit of a wider interrogation point. What that also does is gives us minimal clogging. This is what they look like. So we have the sheathless instrument. Basically, we have one side of the fiber is bored into like a conical that comes into the smaller area where it's the flow cell of 50 by 50 by 100. The illumination part here is about 100 micron. The sheath instrument, on the other hand, now has the same upper part, but now we have sheath flowing through to give us an 18.6 micron pore. And that allows it for a much more concentrated sample to go through because now we have something that will force the cells into a single alignment. The laser beam here is much smaller. It's more focused, and that allows for a much better resolution of the sample. This is what it looks like inside, and we're actually just across the hallway from here. This is the sheathless instrument, which has 3 bottles at 60 ml. The sheath instrument, on the other hand, has 2 bottles. One is the sheath, and the other one is the waste. Both of them have single tube acquisition points, and we use the microcentrifuge tube, 1.5 ml. Both of them also have access to the filters here, where you can change them to whatever suits you, as long as they are excited by the 488 or the 633. Very small footprint, and you'll see it if you go across. Only 14 pounds in weight, so it will go with you everywhere. 2 laser configuration. We have the 520, 585, 635 long pass, and the 760. And we basically are able to acquire PITC PE, PERSI PSI 55, PE Sci 55, and PE Sci 7. So you can have them all blue, or you can have 3 blue, 1 red. The red could be either an APC Sci 7 or APC, just switch them around. Or you can run 2 blue, 2 red if you wish. So this is something that is at will. You do not have to think about switching on a hardware, switching off a laser, or anything like that. You just put your fluorochromes and antibodies into the tube and start acquiring. So basically what it is, it's an affordable instrument, and it's very portable. It's an easy to use instrument. Sheathless or sheath instrument, basically what you have when you have the sheathless is simplified maintenance and reusable samples. Very small footprint. It will fit perfectly into a very busy lab, or even in a hood if you want to. So with the small waste that we have, it is dramatically decreased by a hazard waste. Much smaller sample volume. We can go down to 50 microliter in order to acquire a sample. Reusable samples, that is on the HPC 100 only. Reduced antibody and reagents, because now we can acquire a very low concentration of sample. And then the last one, I think, is the most important, my own, always accessible to me. I don't have to walk across the campus to run flow cytometers. So with that, I would like to turn it over to Dr. Kristina, and she's going to tell us about the exciting work that they're doing in Africa.
Thank you. So we will switch gears a little bit. So you've heard the technical aspect, and now I'm going to tell you what this. You can't hear me? Okay. So now I will tell you a little bit more what you can use this instrument for. So I'm an HIV researcher at UNC, and I'm particularly interested actually in pediatrics. And so those are very small samples, so we routinely do flow cytometry and run 10, 12 color panels. So that instrument would not fit this, but when I saw this instrument, I saw the use for a certain purpose, and that is for studies in Africa, where it's really ideal. So in Africa, as you know, it's still the epicenter of the HIV epidemics, but there are also a lot of other major health concerns. And one of the Millennium Developmental Goals is actually to reduce maternal mortality by 75% in the year 2015, which we have right now. And so why is it a big problem? So it's actually a lot of women die during pregnancy or childbirth, and in countries like the US, it might only be 1 in 4,000 to 5,000 women, but if you go to sub-Saharan Africa, it's really 1 in 30 women. So it's really a major problem. And so one of the main goals by the WHO and several non-profit organizations is to reduce maternal mortality that is related to pregnancy and childbirth. And we really made great strides. So we actually managed to reduce it by 50%, but we have not reached the goal of reducing it down to 75%. And this is just a world map. And you can see where the dark pink violet is, that is in Africa, that's where you have the highest rate of mortality, and that's where you also have the highest rates of HIV, and you will see later how these two are actually linked with each other. So there are multiple ways how you can reduce maternal mortality, and one of the key issues is really to introduce family planning, and that's not an easy task. So there are cultural barriers, so you have to really convince the people in Africa that family planning is important. But even if you can spread that idea, you really need to provide the resources that can actually be implemented. So you really need to establish antenatal and postnatal care as well. So the health care infrastructure really needs to be expanded. And then because there are so many diseases prevalent in these countries, you need to test them for multiple diseases during that time of pregnancy and childbirth, especially for sexually transmitted diseases. And this chart is showing you how the need for contraceptive use actually increased. So this is only showing you areas of the world where contraceptive use is actually not strongly established or wasn't strongly established when that millennium goal was set to reduce maternal mortality related to pregnancy. And on the far left, you can see, I apologize, the pointer is not working. You can see sub-Saharan Africa, and you see in 1919, that's the first bar, only about 40% of the women in reproductive age were actually interested in family planning and use of contraceptives. And we were able to increase that rate by 2012 to about 50%. But you see that the red and the blue are evenly distributed in that bar. So that means that even so we were able to reach about 50% of the women now to convince them that contraceptive use would be a useful means for family planning, only half of them actually have access to contraceptives. And the contraceptive options in Africa that have really taken place are progestin-only contraceptives. And the one that is most prevalent is DMPA or Depo-Provera, as you may know it, and that's a depo-methoxyprogesterone acetate. And it is very effective because it's long-acting, so it can be injected. You come every 3 months, it's injected into your arm, so it has a really high acceptance rate. But 3 months is still pretty frequent if you think about it. It may not be frequent for you, but if you think about Africa, where there is no infrastructure and women actually have to walk to the clinic. And that's the same in certain parts of Asia or other countries. So if they have to walk a couple of miles, even 3 months, coming every 3 months for that shot is a problem. So in more recent years, Jadel has been introduced in Africa. And that's also a progestin-only contraceptive, and that's actually a subdermal implant. So the subdermal implants are more accepted than the intrauterine devices. And that's really the advantage of Jadel, is that it's actually has efficacy for 5 years. So you implant it into the arms, it's really a minor procedure, and so it has found more and more acceptance. So these are two very commonly used contraceptives now. But then after they were introduced, suddenly we became aware that there are several problems that nobody really thought about. So one of the goals was to reduce maternal mortality. But then, so we were able to introduce contraceptive use and family planning. But then suddenly there were those epidemiological studies that raised concerns that maybe the use of DMPA, which was one of the first contraceptives, is associated with a higher risk of HIV infection. And why would that be? And the studies are really controversial. There are some studies that show an increased risk and other studies that could not confirm it. But what has really been shown is that some women that take the DMPA, they show increased activation, and they have increased target cell numbers for the virus. So the virus HIV likes to infect CD4 T cells, and they need to be activated, so they need to express a certain co-receptor that is CCR5 that's only found on activated cells. And Depo-Provera has been shown to increase the frequency of those cells and increase them in the female genital tract. So that's very important if you think about it, because women are the group among in the population that is the fastest rising group of HIV-infected people. So, and sexual transmission is still the most common route of HIV transmission. So we really have to prevent a further increase of HIV infection. And this is just to show you like why that really is a problem. So on the left side of this graph, the African continent, the darker the color, that is where DMPA is actually used. And you see like really in Southern Africa, we were really successful, the WHO, the Gates Foundation, others, to introduce DMPA. But then if you look at the right Africa map, if you see the size of the circles, that indicates the incidence of HIV in those countries. And you can see that in sub-Saharan Africa, especially in South Africa, HIV incidence rates are still between 10 and 20%. So if DMPA may even increase the risk of HIV infection, that would be really detrimental. So, but there are really then two questions that we need to address. So we have HIV negative women, but because incidence is so high, they are at risk of acquiring HIV. And so if you give them DMPA, do we increase their risk even further? But then we also have the group of HIV-infected women that are also interested in family planning now, because they have learned that HIV can be vertically transmitted, and so they don't want their kids to be infected with the virus, so they also want to take contraceptive. And so in those already HIV-infected women, is there also a risk that they could spread the virus and transmit it to their male partners more frequently? And while they are getting antiretroviral therapy and might be completely suppressed in the blood for the virus, if you look in genital secretions, they will still intermittently shed. So if there is immune activation, there is a potential that the virus load in genital secretions could be higher and transmitted more frequently if these women decide to take DMPA. And these problems have really only been described for DMPA. They have not been shown to occur if you use contraceptives like Jadel. So then the question is, so why not just switch over to Jadel? It's really not that easy to convince the population in the first place, so it takes a lot of community work and outreach to get these methods introduced. But in the last 2 years, it has become apparent that Jadel may actually cause another problem, because these are drugs that we are giving people, and HIV-infected women are already taking antiretroviral drugs. And if you think about how drugs are being metabolized in our body, there are certain organs like the liver where a lot of the metabolism takes place, and there is redundancy in the enzyme systems that are metabolizing these drugs. And what has actually been noted is that one of the HIV drugs, efavirenz, interferes with the efficacy of Jadel, of the levonorgestrel. And so that is shown in that little graph. So the red line shows you the concentration of the contraceptive drug in the blood in a woman that is not on antiretroviral therapy. The blue line shows you what the actual drug concentration is if that same woman is taking efavirenz. So what the problem is, that Jadel could actually increase the percentage of unwanted pregnancies. So these women are HIV infected, they are taking antiretroviral drugs, and now they decided to take Jadel. But if there's drug interference, they may actually not be protected from pregnancy and have higher pregnancy rates despite being on a contraceptive. And so these are really complex problems that need to be addressed. And so there's one clinical trial that is going on right now where a clinician from UNC, an OBGYN, decided she wanted to do a trial in Africa. And she just to simply show you the scheme, so she enrolled HIV negative women and HIV positive women. And these two groups of women were then divided and were receiving either DMPA or Jadel. And then we are following these women for 2 years. And so we get samples throughout these 2 years, and of course we test them for their female hormone levels and for the drug levels of the contraceptives. And then we test them for immune activation to see, do we indeed see immune activation induced by contraceptives? And if they are HIV infected, we also test them for the drug concentrations of the antiretrovirals. And then we test for the effect that may have on either HIV acquisition in the HIV negative woman or in the HIV positive woman is, do we observe increased HIV shedding? And if there is drug-drug interference with Jadel, do we observe increased rates of pregnancies? And the samples that we are collecting are blood samples. We are also collecting hair to measure drug concentrations, and then to really measure what's going on locally, we collect cervical vaginal lavages and cervical cytobrushes. And so we are doing this study at our partner institution at the UNC Project Malari, and Jennifer Tang is the OBGYN that leads that study, and Meena Hosseinipour is the clinical director. And she has been there for over 10 years. And in the middle, you see Frances Martinson, who's heading the site in Malari, and Irvin from UNC, who has helped set this up. And at the bottom, you see like really the group of people that has been working there over the years with Charlie Vanderhorst and several other people. So there's really a big collaboration going on between UNC and UNC Project in Malari to train people on site and be able to process samples there and perform clinical trials. And this is just one picture that shows you actually the clinical lab that was set up there. So it's really modern, and it's very well equipped for sample processing and storage. It can perform normal blood analysis, CBCs, Chem20. The people there have been trained in virology. They have really nice PCR setup labs for HIV testing. They have microscopy rooms for malaria testing. In the last 2 years, they got a beautiful pathology lab for cancer research. And in this lab, they can also do some immunology assays like ELISA, CD4 counts. But immunology has really not been developed very much at that site yet. And but for this clinical trial, we really needed to do some of the analysis directly in Malari, because we wanted to go one step further and not just look in the blood, because that will not tell us what is really going on in the female genital tract. We needed to look locally. And so we wanted to look at immune activation by just measuring soluble markers in lavages and in plasma. And so you can just store those samples and do them whenever by ELISA or multiplex analysis. But the cellular markers of immune activation, if you want to do that in the blood and in the cytobrushes, you really need to do the analysis right away. PBMCs from the blood you can freeze. Cytobrushes have so few cells, there's no way you can freeze them and recover them, so those assays needed to be done there. So they asked if I could help them, and they said they have a flow cytometer. So I said, well, if you have a flow cytometer, no problem, you can do it. And then I went there, and then I was really shocked, because the instrument that was there, and I don't want to name the manufacturer, was no longer under service contract. You could use 3 different fluorochromes maybe. It was operating with a software that you cannot even get anymore. You couldn't do any compensation. You couldn't, when you saved the files, you had to pretty much write down beforehand what you did, because it was only a number, so you would never know what you did. And the instrument would break down at least 3 times during the day and used enormous amount of sheath fluid. So even with a few samples that we could run, I had to replace the sheath fluid, and that was really like a big bottle, like a gallon at least, twice a day. And so, but still that's what they have. that's what we have to work with. So I tried to set up some panels for immune activation, and because we couldn't do any compensation, I said, well, you first need to set up a panel just with CD348, and you will always see those populations, and we can somehow assign the parameters and make it work. And then we look among the CD4 T cells, which are the target cells for HIV, for activation markers like CCR5, CD69, or we look for other activation markers like CD38 and HLA-DR. And so I prepared like a really basic scheme like on how they can gate, and you're probably familiar with this, by forward and side scatter, where the populations are, where the T cells are, and where the activation markers should fall. And then we tried to do it on that old instrument, and this is how it looked. So the forward side scatter, that all looked okay, but as you can see, for PE, which was CCR5, we got like a single peak. I mean, there should have been two, so there was nothing really we could do. You couldn't set a gate, or you didn't know what is positive, what is negative. There wasn't a good separation. And so I really never felt comfortable with the set of data that we obtained. And it was even worse if we looked at a panel that had CD38 in it, because CD38 is a marker that is really like a continuum, so you don't get really like defined populations. And you can see like we actually got that autofluorescent tail that is never good if you see that in a flow plot. But that was what I could work with. That was the best way we could get the panels to work on that instrument. So I came back and I was really disappointed, and I felt like kind of down because I had said, yes, we can do it. And then I went there and I thought, we really cannot do it. And then I came back, and just by chance, our flow core at UNC just had a demo by Handiam. And when I saw that instrument, all I could think about was, this is it. This is what we need for Africa, something that is small and simple and sturdy and can be used on the bench, and where you can really train people very easily. And this is at UNC where we had the demo then, and so you can really see the instrument is as small as a laptop. And this is like the user face that you will see on the instrument. So really on the top panel, you have everything is there. You have your on-off switch, you see if the laser is on, you have the fluidics reservoirs, and then on the right are the command tabs, and there are only like two pages that you switch between, is the experiment and the settings. So very, very straightforward to set up. And this is how it looks then. So the interface is very, very easy. And you can save templates, so you can actually load an experiment just like on any other flow cytometer. So I thought, our colleagues in Malawi, they haven't done that kind of analysis, so we could set up templates, we could save them, and then they can just open it and go from there. And the way you calibrate it is you use beads just like you use on other flow cytometers, and as you can see, the beads, they have very nice narrow peaks, so you can really easily set up the instrument, and you do it once in the morning and you're done with it. It's really nice. And there is some compensation, and again, you set it up once, and really from day to day, there's very little variation. It's very sturdy. So all that really convinced me that that would be a useful instrument for Africa. And if you don't want to use the beads, you can use single colors, and as you can see here, I think I just used PE, and it really only comes up in the top right panel and then the bottom middle panel. When I look at PE, there's no spectral overlap there. It doesn't leak into any of the other channels. But what I had to get used to was the gating. So you have like a high background, and then you have to gate on the top population. This is where really like your lymphocytes are. But in the newer instrument, I've learned now that's actually no longer the case. And again, it's just something you need to get used to, and then it's fine. Once you know it, it works really well. It uses a very small volume for blood. It's just 50 microliters. If you want to dilute your sample, you can give this in You can type it in, again, really easy setup, and then you just start your run. And you can also, if you want to, you can name the sample, you can assign the parameters just like in the other instruments, and then you run it. And what we learned is because the flow rate is lower on the older instrument, we used 100 microliters for blood. If you wanted to look for like more populations that are not as frequently found in the blood, like dendritic cells, we would acquire 300 microliters. And then for the cytobrushes, we would really acquire the maximum volume just because there are so few cells in these samples. And this is just one panel, and I know it doesn't look great, but I really wanted to show you like how I was able to train the people in Africa as well. So I took snapshots of the computer, and this was a T-cell panel. And so we gate on the lymphocytes, then we adjust the settings so that it looks more like a flow plot you're normally used to seeing. And then in the bottom right corner is the CD3, CD4 cells, and then you can look at your other markers like CCR5, CD69. You can look at them in combinations, and you get really nice populations. And we did that for a couple of panels, like even the nasty panel that I showed you before with CD38 and HLA-DR, you can get now clear populations. You can look at memory populations. All the panels that we tested came out really nicely on this instrument. And so SUA was actually really helpful. We set up all these panels. These are pretty easy panels, but we set them up at UNC, and then I went down there to Africa and we set it up there, and I was really able to train the people within a week. Because it's so easy to set it up. And this is the software that is loaded on the instrument. And again, it's very straightforward. You can gate on your populations. And now, because we have like at least 4 fluorochromes that we can use, we can look at CD3 and CD4, and then at least at 2 other markers that might be important for CD4 T-cell activation. If you want to do other immunological studies, you can indirectly look at the CD8s by calling them the CD3 positive, CD4 negative population. So you can get quite a good number of data out of it, and you get a similar analysis in the cytobrushes. So overall, and again, even for the software, you can set up templates, and that's what we did. And the people, it's the Novo software, they are also very helpful. They set up internet training seminars with you. And then you can set up your templates. And so now our colleagues in Africa, they acquire the samples. They only have to do minor adjustment in compensations or the populations, and then they plug it into the analysis templates. And then they send the files via Dropbox to us. And if you want to, you can still analyze them again. They can send raw data or analysis data. So I think the advantage is that instrument, it's very small, it's very user-friendly. The training period is really short. Like Sua said, there's no sheath fluid. So the newer instrument may have sheath fluid, but still, really you have those tiny. In the old instrument, we have 60 ml bottles. Now we have 150 ml bottles. It's no comparison to the larger flow instruments. So you really save on reagents, you save on waste, all these things that we may not consider important, but if you are in Africa, those factors are very, very important. The software is easy to use, but it's compatible with FlowJo or other softwares if you already have them, so it doesn't really matter. The other big advantage is that because they are using fiber optics, it's a very sturdy instrument. It weighs almost nothing. It comes in a carry-on, so you can pull it behind you. And so you can really move it from this lab bench to the next lab bench, or if you have an outbreak, you can pack up the instrument, you can go to the village, you can set it up there, and you don't have to worry about realigning the laser. And it is relatively cheap, so which was another big advantage. So I could actually convince our CIFA that would be a very useful adjustment, and the people in Africa really like it. there are some disadvantages, and again, I think with the newer version that is out there now, that may no longer be a problem. So if you have cytobrushes where you have few cells, you want to acquire all the cells that are there, and that sometimes took maybe like 10 minutes per sample. So it's not, if you have a high throughput, that may not be ideal. And then again, if you have software updates, it can be done over the internet, but again, internet is not always all that great. So in those countries, so you have to find a good time period where the internet is actually able to handle and upgrade. And so normally we do that overnight then, and that works well. The other problem that I see is that there are no field specialists in Africa. So if you need service, you need to send it in and get it to a place. But so far, we set up the instrument in October. So far, we didn't need any service. And the few times they had a problem, they were able to really easily communicate via email with either SUA or Matt or the software people. So that's, I think that's one of the big examples where I really see where these instruments are extremely useful and handy, just as the name says. It's a handy instrument to have. Thank you. And so, yeah, I should probably acknowledge again, so that instrument was really the study, the clinical trial that is ongoing, so I cannot show you any data. It's really led by Jennifer Tang. It's co-funded by the CDC. It's also funded by the NIH. Through a K Award and a Fogarty Award to Jen, and the CIFA provided us funding for instruments, and so we are in constant exchange with them to get this going.